Imagine looking back in time, not just a few years, but over 13 billion years to the dawn of the universe. In this cosmic nursery where the first stars and galaxies were just beginning to flicker into existence, you wouldn't expect to find monsters, but the James Webb Space Telescope just found one. Peering into the early cosmos, just 700 million years after the Big Bang, Webb focused on a galaxy designated QS01. At its heart, it found a supermassive black hole weighing in at around 10 million times the mass of our Sun. But the size alone isn't the whole story. This black hole is so massive, it accounts for a staggering 10% of its entire galaxy's mass. For comparison, the black hole in our Milky Way is less than 1/100% of our galaxy's mass. And even more surprisingly, its host galaxy is chemically pristine. It lacks the heavy elements or metals that are forged inside stars. This creates a huge problem for our standard theories. The fact that this galaxy is so unspoiled by metals means very few stars have lived and died there. So if there wasn't much star formation, where did this monster black hole come from? The traditional theory says black holes start from the collapsed cores of giant stars and grow slowly. But QS01's galaxy didn't have enough stars to even create the seed, let alone enough time for it to grow. Another idea was that a massive cloud of gas could collapse directly into a heavy black hole. But even this predicts a frenzy of star formation nearby, which would have polluted the galaxy with metals. Again, the evidence from Webb doesn't match. This leads us to a third, more exotic possibility: primordial black holes. These are not born from stars or gas clouds, but are hypothesized to have formed from extreme density fluctuations in the universe's first second of existence. They were born before the first stars and galaxies. They could act as the initial seeds, growing silently in the dark, gathering pristine, metal-free gas long before stars had a chance to light up the cosmos. The discovery of QS01 provides the first compelling observational evidence for this primordial origin story. It's a fossil not just from the dawn of galaxies, but potentially from the very first moments of the universe itself. It's rewriting the first chapter of cosmic history, telling us that giants may have walked among the infants. Thanks to Webb, we're learning that the early universe was far more dramatic and far more surprising than we ever dared to imagine. Every second, Earth is bombarded by cosmic rays, tiny high-speed visitors from outer space. They are the background noise of the universe. But sometimes, the universe doesn't whisper, it screams. On October 15, 1991, scientists recorded a scream so loud, so energetic, that it seemed to violate the very rules of reality. It was a single proton, and it carried the kinetic energy of a baseball thrown at 60 miles per hour. Imagine that power, the wallop of a fastball, all packed into a particle so small you could fit trillions of them on the head of a pin. On a clear night in the Utah desert, an array of detectors called the Fly's Eye experiment registered a flash brighter than anything seen before. When scientists ran the numbers, they were stunned. The energy was so impossibly high, it defied explanation. In the logbook, one physicist simply wrote a note, and a legend was born. It became known as the "Oh my God" particle. But this incredible discovery created an even bigger problem. You see, there's a cosmic speed limit. The universe is filled with a thick fog of ancient light left over from the Big Bang. As a high-energy particle travels through this fog, it loses energy. Physics dictated that a particle this powerful couldn't have traveled from a distant galaxy. It had to have come from our own cosmic neighborhood. But when astronomers looked, there was nothing. No exploding galaxy, no cosmic engine that could have possibly produced it. The particle's origin was a complete mystery. For decades, this remained a frustrating puzzle, but the universe kept sending us clues, and scientists built new, more powerful observatories to catch them. In 2012, deep beneath the Antarctic ice, they caught another ghost. This time, the detector was IceCube, a massive observatory threaded through a cubic kilometer of solid ice. And the messenger was a different kind of particle, a high-energy neutrino, so elusive it could travel through entire planets without leaving a trace. This one was so energetic, researchers nicknamed it Big Bird. But unlike the oh my god particle, this ghost didn't arrive alone. As astronomers traced its path back across the sky, they found a smoking gun. At the same time Big Bird was detected, a distant galaxy had flared up. It was a blazar, a cosmic powerhouse where a supermassive black hole at the galaxy's core shoots a jet of particles directly at Earth. For the first time, scientists had a prime suspect for one of these ultra-high-energy messengers. While the blazar is the likely source for the Big Bird neutrino, the origin of the original, far more powerful oh my god particle remains unsolved. Each detection is a new chapter in a cosmic detective story, reminding us that the universe's most violent events are writing messages across the sky, and we are only just beginning to learn how to read them. Deep beneath the Franco-Swiss border lies the most complex machine ever built, the Large Hadron Collider. It is a 27-kilometer ring of science, engineered for a single purpose: to unlock the fundamental secrets of the universe. Born from a dream in the 1980s to recreate the Big Bang's first moments, its engineering challenge was staggering. Thousands of superconducting magnets, cooled colder than deep space, generate immense fields to steer two beams of protons in opposite directions. Accelerated near the speed of light through a near-perfect vacuum, these protons circle the ring over 11,000 times per second. Then, at 4 specific points, the beams are crossed, triggering up to 1 billion proton-proton collisions every single second. All this for one primary quest: the hunt for the Higgs boson, the missing piece of our fundamental theory of physics. The theory proposed an invisible energy field permeating all of space. As particles travel through this Higgs field, they gain mass. The more they interact, the heavier they become. To prove this field exists, you have to hit it hard. The LHC's collisions provide just enough energy to knock a particle loose from the field, the Higgs boson itself. The problem? The Higgs is a ghost. It exists for less than a zeptosecond before decaying into a shower of more stable particles. You can never see it directly. You can only see its shadow. 2 gigantic detectors, Atlas and CMS, act as multi-story digital cameras, built to see these shadows by tracking the debris from every collision. For years, scientists sifted through trillions of collisions, searching for a tiny statistical bump, a specific energy signature. It was like listening for a single voice in a billion-person stadium. Then, on July 4, 2012, the announcement came. Both experiments had seen it, a definitive bump at an energy of 125 giga-electron volts. The ghost was found. This was more than a discovery. It was a triumph of global collaboration that confirmed our understanding of reality and opened the door to new mysteries. The LHC's ultimate purpose isn't to conquer the universe, but simply to ask it how it works and to listen patiently for the answer. For centuries after their discovery in 1610, Jupiter's 4 largest moons were just curiosities, celestial clockwork in a frozen, desolate part of our solar system. The search for life was a search for worlds like our own, warmed by a sun. Jupiter's moons, Io, Europa, Ganymede, and Callisto, were believed to be cold, dead, and irrelevant. That all changed in 1979. When the Voyager spacecraft flew past, it sent back images that stunned the world, and the most enigmatic of all was Europa. Its icy face was not ancient and cratered, but smooth and young, covered in a vast network of mysterious cracks and reddish bands. It looked less like a moon and more like a fractured eggshell. Scientists realized that Jupiter's immense gravity was constantly squeezing and stretching Europa, generating a powerful internal heat through tidal friction. The sun was no longer the only source of warmth. A new, radical idea emerged. What if Europa's internal furnace was hot enough to melt its ice from below? The Galileo mission in the 1990s confirmed it. By measuring the moon's magnetic field, it found definitive evidence of a global, salty, liquid layer beneath the ice. The ocean was real. An entire world of liquid water, perhaps twice the volume of all of Earth's oceans combined, was hiding in plain sight. Suddenly, the definition of a habitable world was rewritten. The three essential ingredients for life are liquid water, the right chemical building blocks, and an energy source. Europa appears to have all three. Its ocean, protected from radiation by a thick icy shell, has likely existed for billions of years. Chemicals delivered by comets would have mixed into its waters. And the energy? The same tidal heating that melts the ice could power hydrothermal vents on the ocean floor. Here on Earth, such vents are oases for life, thriving on chemical energy in total darkness. Could a similar genesis have occurred in the silent, dark waters of Europa? Or even Ganymede, Jupiter's largest moon, which also shows evidence of a massive subsurface ocean? For decades, these ocean worlds remained a distant dream, but now we are going back. ESA's JUICE mission is already on its way to perform a grand tour of these icy moons. And following close behind is NASA's Europa Clipper, a mission designed specifically as reconnaissance for life. Clipper will perform dozens of daring, low-altitude flybys, using ice-penetrating radar to confirm the ocean's depth and scanners to analyze the surface chemistry. Its primary target is one of nature's greatest gifts, plumes. We have evidence that geysers of water vapor may be erupting from Europa's surface, launching ocean material directly into space. If Clipper can fly through one of these plumes, it can taste an alien sea without ever needing to land. From simple points of light in Galileo's telescope to the most compelling targets in our search for life, Jupiter's moons hold one of the solar system's greatest secrets, an answer to the most profound question we have ever asked. Are we alone? We are no longer just looking. We are finally on our way to find out. Between the fiery ambition of Mars and the colossal might of Jupiter lies a silent, sprawling cosmic highway. This is the asteroid belt, a vast ring of debris where millions of objects, ranging from dusty pebbles to dwarf planets, endlessly orbit our sun. For decades, we imagined it as a chaotic, impassable field. The reality, however, is far more empty. The average distance between asteroids is over 500,000 miles. They are less like a gravel road and more like lonely islands of rock and metal, separated by an ocean of vacuum. These are the leftovers of creation, remnants of a planet that never was, torn apart by Jupiter's immense gravity. But this cosmic rubble doesn't always stay in its lane. A gravitational nudge can send an asteroid tumbling inward on a potential collision course with other planets, including our own. Earth bears the scars of these encounters. The most famous is the Chicxulub impactor, a 6-mile-wide behemoth that struck the Yucatan Peninsula 66 million years ago, ending the reign of the dinosaurs. More recently, in 2013, the world watched as a 60-foot object streaked across the skies of Chelyabinsk, Russia, exploding with the force of 30 atomic bombs, a stark reminder that our solar system is an active place. But not everything that crosses our path is from our own neighborhood. Some visitors are from much, much farther away. On July 1st, the Atlas Survey Telescope in Chile spotted something extraordinary. Named 3I/Atlas, it was only the third interstellar object ever confirmed to have entered our solar system. What makes astronomers certain? Its trajectory. The object follows a highly hyperbolic orbit, meaning it isn't bound by the sun's gravity. Its path is so extreme that it massively outpaces the two interstellar visitors that came before it, Oumuamua and Borisov. This visitor is not just passing through, it's screaming through space. And unlike the others, this one is huge, estimated to be around 9 to 12 miles in diameter. It's a true cosmic giant. Shortly after its discovery, signs of a comet-like coma and tail became evident. This wasn't just a rock. It was a cosmic snowball, carrying the chemical signatures of its home star system, countless light-years away. While it poses no threat to Earth, its journey will bring it just inside the orbit of Mars before it slingshots around the Sun and heads back out into the void. For scientists, 3I/Atlas is a monumental opportunity. It's a tangible connection to another star system, a free sample delivered right to our doorstep. We can't send a spacecraft to meet it. It's simply moving too fast, but our telescopes can study it intensely, and it's likely just the beginning. The reason we are suddenly finding these interstellar wanderers is that our technology is getting better. With new observatories like the Vera C. Rubin coming online, we are poised to discover many more. As one astronomer put it, get ready for 4I, 5I, 42I. From the familiar rubble of our own asteroid belt to these giant messengers from distant stars, each object reminds us that we are part of a vast, interconnected cosmos with new discoveries waiting just beyond the next sunset. Let's begin a journey to understand true cosmic scale. We start at home, on Earth, a world that seems vast to us. But the first step on our journey reveals our local giant, our own sun. It is a roaring furnace so immense that over 1 million planet Earths could fit comfortably inside. The sun is a true monster, accounting for 99.8% of all mass in our solar system. By any measure, it is a king. But now we must leave this king behind. Our real journey takes us 20,000 light-years away, past shimmering nebulae and stellar nurseries, to a crowded star cluster in the constellation of Scutum. Here, we find a star that dwarfs our own sun so completely, it forces us to reconsider everything we thought we knew about size. Its name is Stephenson 218. It is the largest star known. Its size is difficult to comprehend, with an estimated radius 2,150 times that of our Sun. If you were to place it at the center of our solar system, its surface would extend beyond the orbit of Jupiter, reaching all the way out to Saturn. Any planet in our inner solar system would be nothing but a vaporized speck deep within its stellar atmosphere. Its volume is so immense that nearly 10 billion of our suns could fit comfortably inside it. So why is it so enormous? Stephenson 218 is a red supergiant, one of the most luminous ever found. It is a star nearing the end of its life. For millions of years, it has burned through its fuel at a furious rate. Now, the immense outward pressure from its intensely hot core has inflated its outer layers to this incredible size. Despite its size, it's actually quite cool for a star, with a surface temperature of only about 3,200 Kelvin. This is what gives it its distinct fiery red color, but it compensates for this low temperature with sheer scale, shining with the light of almost 500,000 suns. And because it lives so furiously, it will die spectacularly. A star this massive won't simply fade away. When its fuel finally runs out, gravity will win the final battle. In an instant, the star's colossal outer layers will come crashing down onto its core, triggering an explosion of unimaginable violence, a supernova. For a few weeks, Stephenson 218 will outshine most of the stars in our galaxy combined, blazing as a beacon across the universe. Then, silence. The great titan will be gone, and in its place, its core, crushed by its own immense gravity, will almost certainly collapse into a stellar mass black hole, a silent, invisible tombstone marking where a giant once reigned. But this death is also an act of creation. The explosion will seed the surrounding cosmos with the heavy elements forged in its heart, the very gold, carbon, and iron that will one day form new stars, new planets, and perhaps new life. The ghost of the universe's largest star will become the building block for the future. For as long as we have looked at the stars, we have known that the cosmos is not always a gentle place. The same impacts that delivered water to our world also ended the age of the dinosaurs. For all of human history, an asteroid on a collision course was a threat we could only watch. We had no defense, no way to fight back. Until now. This is the story of DART, the double asteroid redirection test. The mission's objective was as simple as it was audacious: to prove, for the first time, that humanity could deliberately change the motion of a celestial object. It was a test to see if we could one day protect our planet by giving a dangerous asteroid a tiny nudge, years before it could ever become a threat. The target was a binary asteroid system named Deimos, located millions of miles from Earth. It's important to know, this asteroid system posed absolutely no threat to our planet, which made it the perfect, safe firing range for this historic experiment. The mission-specific bullseye was the smaller of the two asteroids, a moonlet named Dimorphos, as it orbited its larger companion. The plan was a showcase of kinetic force. On September 26, 2022, the DART spacecraft, about the size of a vending machine, slammed into Dimorphos at a blistering 14,000 miles per hour. The world watched as the final images streamed back before the screen went black. The impact was a success. But the real question remained: did it work? Did we actually move an asteroid? The answer, confirmed by NASA after weeks of observation from telescopes across the globe, was a resounding, historic yes. Before the impact, Dimorphos took 11 hours and 55 minutes to orbit Didymos. The DART team had predicted the impact would shorten this orbit by at least 73 seconds to be considered a success. But the result shattered all expectations. The DART impact didn't just meet the goal, it obliterated it. The spacecraft's collision altered Dimorphos' orbit by a staggering 32 minutes. The tiny moonlet was pushed closer to its parent asteroid, its orbital path forever changed by a craft built on Earth. Scientists found that the impact was amplified. The blast of rock and debris, the ejecta, that was thrown into space from the crash acted like a rocket engine, giving Dimorphos an extra powerful push. This mission marks a new era for humanity. It is a proof of concept that solidifies planetary defense as a tangible reality. As NASA Administrator Bill Nelson stated, "This mission shows that NASA is trying to be ready for whatever the universe throws at us. For the first time in the history of our world, we have demonstrated that we are not just spectators. We have the power to protect our home." Look up at the night sky. For millennia, a distant, untouchable ceiling. Today, we see it for what it is, a destination. This is the story of our future. A tale written not in ink, but in energy, measured on a scale of cosmic proportions. We stand today as a Type 0 civilization, drawing power from the fossilized remains of ancient life. But the dawn of the next stage is on the horizon. A Type 1 civilization is a planetary one. It has achieved complete control over the energy of its home world. Imagine fusion reactors humming in every city, providing limitless, clean power, vast solar arrays drinking in sunlight, and the full might of our planet's geothermal and tidal forces harnessed. With this energy, we don't just solve climate change, we master our environment. Resource scarcity becomes a concept for the history books, and a united humanity finally learns to manage its cradle. But a cradle is meant to be left behind. This planetary energy is the launchpad for our next great endeavor, conquering our own solar system. This is the journey to becoming a Type 2 civilization, one that commands the power of its parent star. The feasibility is a matter of engineering, not fantasy. The moon becomes a shipyard. Mars is terraformed under a new sky. We will mine the asteroid belt for the building blocks of new worlds. But the ultimate tool of a Type 2 species is the Dyson Swarm, a megastructure of orbiting collectors, a net cast around our sun, catching a significant portion of its colossal energy output. With the power of a star at our command, humanity transforms. We are no longer bound to a single planetary surface. We become a solar species. And then, with our system mastered, we will look out, past the edge of our own small solar neighborhood, to the silent beckoning lights of other suns. The ultimate challenge, reaching another star system. This is the graduation to a Type 3, galactic civilization. The sheer distance is staggering. How do we cross it? The first voyagers may travel on slow boats, generation ships, self-contained worlds on millennia-long journeys. But with the immense energy of a Type 2 civilization, we can do better. We can use that power to fire continent-sized lasers, pushing vast light sails to a significant fraction of the speed of light, cutting the journey from thousands of years to mere decades. The pattern is clear. Each great leap, from planetary to stellar to galactic, is a leap in our ability to gather and wield energy. Energy is the currency of the cosmos. It is the force that will allow us to rewrite our physical limitations, to settle new worlds, and to ensure that the story of humanity is not a short tale on a single blue world, but an epic written across the stars. When we look out into the cosmos, we see a vast, silent tapestry. To grasp its scale, we must recalibrate our minds. Our Milky Way galaxy, 100,000 light-years across, is just one of hundreds of billions. Galaxies themselves gather into clusters, and clusters string together into immense filaments, forming a great cosmic web. But for all this structure, our understanding of the universe rests on one fundamental pillar, the cosmological principle. This principle states that on the very largest scales, the universe is essentially the same everywhere. It is homogeneous and isotropic. If you zoom out far enough, the lumpy cosmic web should smooth out, like looking at a beach from so high up that you can no longer see the individual grains of sand, only a uniform stretch of shoreline. Our models are built on this assumption. They even give us a number, a theoretical speed limit on size. No single connected structure should be larger than about 1.2 billion light-years across. And then, we found them. First, we must understand the quasar. A quasar is a cosmic lighthouse, a beacon of unimaginable violence and brilliance. At its heart is a ravenous supermassive black hole, devouring so much matter that the disk of infalling gas and dust heats up and outshines its entire host galaxy by 1,000 times. Because they are so bright, we can see them from across the observable universe. They are the lampposts of the cosmic dawn. And in 2013, astronomers found a collection of these lampposts that defied belief. A congregation of 73 quasars, clustered together in a region of space so vast it shattered our sense of scale. They called it the huge LQG, or Large Quasar Group. Its size is almost incomprehensible. It stretches 4 billion light-years from end to end. If you could travel at the speed of light, it would take you 4 billion years to cross it. This is not a string of galaxies. It's a colossal structure more than 3 times larger than the theoretical maximum size allowed by the cosmological principle. It is a cosmic anomaly, a feature on the map of the universe that our rulebook says should not exist. The huge LQG and other similar structures since discovered presents us with a profound challenge. Is it a 1 in a trillion statistical fluke, a chance alignment of lighthouses that only appears to be a single entity? Or is it a genuine, gravitationally linked structure, a cosmic titan from the early universe? If it is real, then our fundamental assumption, the smooth, uniform nature of the cosmos on the largest scales, might be wrong, or at the very least, incomplete. These structures force us to ask new questions. Did the universe form structures more efficiently than we thought? Does a force or a mechanism we don't yet understand operate on these immense scales? Large quasar groups are not a failure of our theories. They are the sign of science working perfectly. They are cosmic question marks etched in light, pushing the boundaries of our knowledge and reminding us that in the grand, silent theater of the universe, there are still titans hiding in the dark, waiting to be discovered. From the moment we first looked up at the glittering tapestry of the night sky, a single profound question has echoed through human history. Are we alone? For millennia, that question was the domain of philosophers and dreamers. But now, in our time, it has become a question for science. With telescopes that can peer into the deepest recesses of the cosmos, We are no longer just guessing, we are searching. And what we are finding is staggering. Not just planets, but worlds. Worlds that orbit in the gentle, life-giving warmth of their parent stars. Consider Kepler 452b, a world some have called Earth's older cousin. It orbits a star very much like our own Sun, but one that is 1.5 billion years older. This super-Earth is larger than our home, with a stronger pull of gravity. One can't help but wonder, if life arose there, what could it have become with such an immense head start? But its age is a double-edged sword. Its aging star now shines brighter, and Kepler 452b may be entering the final stages of a runaway greenhouse effect, a poignant reminder of the fragile window for life. But perhaps we are too narrow in our search. Perhaps life doesn't need a star like our own. Journey with us then to the system of Gliese 180, a mere 40 light-years away. It orbits a dim, cool red dwarf. Here, the habitable zone is huddled close to the star for warmth. At least one planet, Gliese 180d, a cold super-Earth, orbits comfortably within this region. Life here would be profoundly different. These worlds are likely tidally locked, one side in perpetual day, the other in eternal night. Could life thrive not under a wandering sun but in the endless twilight of the Terminator Zone, that sliver of a world between light and dark? It forces us to imagine biology born of stark contrasts. And then there are the candidates that make us hold our breath. The unconfirmed world of KOI 4878.01. If its existence is verified, it would be the most Earth-like planet ever discovered. It is almost exactly Earth's size, orbiting a sun-like star with a year lasting 449 days. Its calculated Earth similarity index is an astonishing 98%, a true terrestrial twin. Is there a world out there, drifting through the darkness with continents and oceans so similar to our own we might mistake it for home? Does it have its own clouds, its own rain, its own life? We don't have the answers yet. These worlds are impossibly distant, their secrets guarded by a vast gulf of space and time. But they are no longer just points of light. They are destinations. They are possibilities. For now, the cosmos remains silent. But in that silence, there is no longer emptiness, there is potential. And so, we listen, we watch, and we wonder, waiting for a whisper from across the cosmic ocean.